Welcome one and all once again. So, this is the lecture number 2 for on estimation. So now we have some basic definitions. First one is population. So actually, population I have already discussed that what is population. That population is the larger set, larger set of persons or things about which we want to estimate something. So in one of the previous examples, this population was the state of Delhi. It can be actually any larger, as I'm telling, any larger set. Say it may be New York City. It may be any. We can say any state, any city, any such larger population. Okay, so here we can also say that the group of individual under study, it is called population. Okay, so here instead of individual, it may be any another thing. It may be some this study may be regarding the animals also. Okay, so this is a population. Okay, so understudy means that we are trying to estimate something. We are trying to estimate something about this population. Okay, so now, sample, we know what is sample. Okay, a finite subset of this population. Okay. Now, sample size, I have already mentioned that usually, not always, that we denote our sample observations by small case x1, x2, okay, going on up to xn. So this n, okay, this is what we call our sample size. And even simple random sampling, I had discussed that a random sample is one in which each unit of the population. So now you can see this wording, each unit of population. So unit of population means capital X1, capital Xi. So capital X1, capital X2, okay, going on up to capital X and N. Okay, so here capital N, it is population size. So these are our population units. So each population unit has an equal chance, okay, of being there in the sample. So being included in it. What is this? It refers to sample, okay. So if each population unit has same chance, same probability of being there in the sample. Okay. And this probability is independent of the previous drawings. Means drawing here that the previous selection of sample observations. Here drawing means selection. Okay. So this is what we say SRS, simple random sampling. Okay, and here that this probability is independent means suppose I have already selected say 10 sample observations, then my selection of 11th sample observation. Okay, these selection of 11th sample observation, selection or drawing. Okay, it should be independent of the previous 10 sample observations. Now, uh, we have population and we have sample now. Means we have two things. One is one is population and another is sample. We have two things. One is population. So here, this is the population. Okay. And what are these? This is a sample. Okay. So these are our samples. Now, both population as well as sample, they will have their statistical constants or measures. Example, this mu and sigma square, they are statistical constants or measures. Okay, you can see. So Mu and sigma square, they are statistical constants which are associated with what? Population. Okay. So mu and sigma square, what we call them? Parameter. Okay. So what is a parameter? That any statistical constant or measure which is associated with population. Okay. And there is another thing now, that is statistic. So any statistical constant or measure which is computed from sample observations or which is associated with sample observation. Okay. Say sample mean, sample variance. Okay. Now, mu and sigma square, they are statistical constants. Okay. Which are associated with what? Population. Okay. And X bar, sample mean, and S square, small s square. Okay. So sample variance, even they are also statistical constants. Okay. But they are associated with what? They are associated with sample. So I will call that these are statistic. Okay, so it is simple thing that we have two things. One is sample, another is population. Both population and sample, they have their own statistical constants. Okay, so the statistical constants of population, okay, we call them parameters, and the statistical constants of sample, they are called statistic. Okay, the plural word is statistics. Okay, now uh, the next thing is, actually here, this is one definition of statistics. There is another definition. Okay, the another definition of statistic, that it is a function of, sample observations x1, x2, xn. Okay, so this thing, actually, by your the knowledge of previous classes, f at x1. So this how we read that this is the value of f at x1, and this is the value of function of x1, x2. Okay, then the function of say x, y, z, means how we read these notations. So this is function of x1, this is function of x1, x2, this is function of x, y, z. So even this notation is also same. This notation is also same, that it is function, of x1, x2, xn, or the value of this. Okay, that tn, x1, x2, xn, the value of this, it depends upon these sample observations. Okay, so this is the another definition of statistic. Okay, that statistic is nothing but a function. Okay, yeah, here we are using the symbol f. Okay, and here we are using the symbol tn. Okay, but ultimately both mean same. Okay, that this is a function of sample observations. Now obviously the x bar and small s square, okay, means the sample mean. So this is x1 plus x2 plus xn by n. So obviously, this sample mean, its value depends upon what? X size means sample observations, or in other words, this sample mean, it is a function. It is a function of what? These sample observations. Okay. Now, S square. This is 1 by n summation xi minus this thing. Even this is also a function of sample observation, because even the values of S square, it depends upon what? X size. Okay, X size. And even X bar further, it depends upon what? X size, sample observations. Similarly, capital S square, that is, uh, okay, so this one, just, yeah, so capital S square. which is 1 upon n minus 1 summation of this. Okay. So even its values, they depend upon xi's. Okay. So that's why sample mean, sample variance, okay, and this capital S square. Okay. So all these, they are examples of statistic. Okay. Now this whole concept of estimation, it is about estimating the unknown parameters. I repeat, this whole concept of estimation, it is about, okay, it is about estimating the unknown parameters. Example, suppose the very first example that I want to estimate the average, average or mean, okay, per day, per day, data uses, average per day data uses for per person, okay, for say New York City, okay, for the New York City. So here, this average per day data uses per person in New York, this I can denote, I can and I will denote by what symbol? Mu. Okay, because this is average, mean. Okay, so here this mu, obviously this mu is not known to me. Okay, because if this mu me is known, means if I already know that what is the average per day data uses. Okay, for example, suppose I know that this mu is say 2.5 GB per day. This is 2.5 GB per day. Then why would I estimate that? Then why would I have take these samples? Obviously, I will take these samples only if I will take these samples throughout the different parts of New York City, only if this mu, the parameter, it is unknown. Okay, even the what's the chapter name? Estimation. So here what we are estimating, what we are trying to estimate, we are trying to estimate the unknown parameters. Okay, so if the parameter is known, then what's the need of estimating that? If the parameter is known, the value of parameter is known. Okay, for example, here 2.5 GB per day. Is there any need to estimate that? No. So we estimate that parameter which is unknown. Okay. So any function of random samples, okay, a random sample that are being observed, okay, means these are our sample observations. Say this, okay, it is called statistic. This I have already discussed that a statistic, it may also be defined as a function of sample observations. Okay, now clearly, a statistic is a random variable, obviously, because these xi's they can have any random value. Now, any random value means these xi's, as I discussed in previous lecture, that this small xi, it can take any capital Xj, means this small xi, it can be any jth population value. My any ith sample observation, it can be my any jth population value. Okay, so it can be this selection is random, or this xi, it can take a random, it can take any population value randomly. Now here we are estimating the parameters, unknown parameters. Here this mu, the average per day data uses. Now I will try to estimate this mu with the help of what? With the help of data uses of these samples. Obviously, means I will take these samples throughout the New York City. Okay, now for these samples, what I will calculate? I will calculate their data uses. Okay, the data uses of these samples. Now, from the data uses of these samples, I will try to estimate the population mean mu. Okay, so here now, if it is used, what is used? A statistic is used. If it is used, what is used? Statistic. Okay. To if a statistic is used to estimate what? An unknown parameter. Okay. Then it is called estimator. Okay, for example, here I will try to estimate this average per day data uses mu with the help of X bar, means with the help of sample average per day data uses of all these samples. I will try to estimate this mu, okay, with the help of X bar. So what will be X bar? This will be the average per day data uses of, say, first sample, second sample, means each sample will have its own X bar, sample mean. Okay, so with the help of sample means, I will try to estimate the population mean. Okay, so obviously this X bar, it is a statistic. Now, a particular value of the estimator is called estimate of theta. Uh, Actually, to denote the parameter, we will be using the symbol theta or gamma. Okay, this is the lowercase gamma or gamma bracket theta. Okay, in our future discussion, uh, we will denote our parameters. Okay, the generic symbols. The generic symbols of a parameter will be either theta or simply it will be gamma or gamma bracket theta. Although this notation gamma bracket theta, it further has a meaning. Actually, this theta is coming from parameter space. But for the scope of actually these things, they are beyond the scope of the present lecture. Okay. So these will be the usual, these are generic or general symbols to denote the parameter. Okay. If I talk in particular that here in this example, what is our theta or this parameter? It is our mu. Okay. So there is another common parameter for us, that is sigma square. Okay. So for us, most of the times we will be estimating either population mean or population variance. Means most of the times, okay, our unknown parameters, the unknown parameters will be either population mean or population variance. Okay. Now, so here what we are looking for, actually we are looking for estimators. Okay. So now the estimator, it should be a good estimator. Obviously, if our estimator is not good, means our estimator is bad, then it will give us a bad estimate of the parameter. Okay, so here we are trying to estimate the parameters and we are trying to estimate the unknown parameters with the help of estimator. Okay, so what is estimator? It is nothing but a statistic, but a statistic when it is used to estimate an unknown parameter. So obviously here we are looking for estimators, and our estimator should be a good estimator. Now, for a good estimator, the statisticians or mathematicians, they have defined some characteristics. So, what are the good characteristics of an estimator? It should be unbiased. It should be consistent. It should be efficient, sufficient. And I will discuss one more characteristic that comes under MLE, the maximum likelihood estimation or estimator. Okay. So one by one, we will discuss all these characteristics. So the first characteristic, unbiased estimator. Now, a statistic means a function of sample observation is said to be an unbiased estimator of the parameter gamma. Okay, if the expected value of Tn it is equal to gamma for all theta coming from this parameter space. Okay, now there is a question you can see. I will strongly suggest that pause a video for a some time and try to answer this question of your own. Okay, after that you can go through this, you should go through this solution, but at first please pause the video and try to answer this question. Now, sample mean is an unbiased estimator of population mean. Actually, this is a correct statement. Expected value of x bar, this is equal to population mean. And now here, this equation, actually this is satisfying that expected value of Tn, it is equal to the parameter value. What is our Tn here? Tn, the estimator, it is x bar. The function of sample values, it is x bar, statistic or actually estimator here. And what is our parameter here? Mu. Okay. So now this equation is true that we had proved in previous lecture. Okay. So what this equation means? This equation means that sample mean, this is unbiased estimator of population mean. Why? Because the expected value of sample mean is equal to population mean. Okay, so that's why first statement is correct. Sample variance. Now, the expected value of sample variance. Actually, we have derived that this is equal to n minus 1 by n times sigma square, which is not equal to sigma square. Now, here, what is our Tn? Tn, the estimator, the function of sample observation, it is s square. And what is our parameter here? It is sigma square. Now, the expected value of sample variance, it is not equal to, it is not equal to population variance, means sample variance, it is not unbiased estimator of population variance. And expected value of capital S square. Okay. So this is equal to sigma square. Actually, all these results, okay, I have proved in the previous lecture. So one must go through that. Okay. Expected value of capital S square. Okay. So here it is mentioned that is equal to sigma square. So now what is our Tn here? What is our Tn? It is capital S square. Okay, and what is our parameter here? Sigma square. And since this is true, means the capital S square, it is unbiased estimator of population variance. Okay, so here statement number A and C are correct. Okay, and B is incorrect. Okay. So now we have a name of this capital S square. We have a name of this capital S square. That is what we call unbiased estimator of population variance. One remark here that here we are having one thing that is what we call sample variance, that is 1 by n summation xi minus x bar square. Okay. Also, this is equal to 1 by n summation xi square minus x bar square. Okay. Now, we will make a distinction between sample variance, small s square, okay, small case s square, and capital case s square. Okay, because in sample variance, there is n here, and in case of capital S square, it is n minus 1. Okay, rest this summation is same. Okay, and one personal suggestion here that please watch the previous video very carefully. Actually, these symbols, okay, mu, sigma, x bar, s square, capital S square, okay, they are actually important. Okay, so one must have the clarity about these symbols. Otherwise, one will be lost in the symbols themselves. Okay. So, uh, mm, we will make a distinction between this small case S square and capital case S square, but most of the foreign authors, means outside the India, they don't make any such distinction. Okay, actually, for those most of the foreign authors, they define this capital S square. They define this capital S square as sample variance. I repeat, for us, we will be taking this expression as sample variance. But as per my knowledge, the foreign authors, means the authors which are outside India, okay, they define this expression as sample variance. For the foreign authors, there is no concept of a small case S square or capital case S square. Okay. Now, if expected value of Tn, it comes out to be greater than the parameter, then we say that this statistic is positively biased, and if it is less, then we say it is negatively biased. And this difference, this is what we call the bias, the amount of bias in Tn. And if this amount is equal to 0, then obviously this Tn, this will be unbiased estimator of parameter gamma. Now, here, yes, uh, expected value of sample variance, it is 1 minus 1 by n into sigma square, and this is now sigma square minus sigma square by n. Okay, so actually I have written the same thing, and this is nothing but this, and this is obviously less than sigma square. Why? Because sigma square, it is a population variance, it can never be negative. This it can be never negative, and even n sample size, it can be never negative. So means this quantity, okay, this is never negative. So sigma square minus something non-negative, obviously it will be less than sigma square. Okay, so means sample variance, okay, it is positively biased estimator because it satisfies this one. Okay, so sample variance, it is positively biased. Okay, and what is this amount, sigma square by n? This sigma square by n, actually this is the bias. Okay, this is the bias. Why? Because expected value of S square, okay, minus sigma square. So what is that? So what is this thing? It is sigma square minus sigma square by n and minus sigma square. So this is nothing but minus sigma square by n. Okay. So this quantity. Okay. Yeah. Earlier I missed this negative. Okay. So actually this whole minus sigma square by n. Okay. So this is the bias. Okay. This thing, bias in the sample variance. Now, yes, this thing. Now, one thing here that usually in our estimation, the distribution of the population is known. I repeat, usually, not always, usually, the distribution of the population, okay, uh, it is known. Actually, the population units, okay, capital X size, they follow which distribution? Means whether they follow normal distribution or they follow Bernoulli distribution or Poisson distribution or any other gamma distribution. So usually this is known. Now we have a sample, okay? It is a random sample, okay, of size n from a normal population. Then this estimator, obviously this t, it is a function of sample observations, x1, x2, xn. You can very well see. So this is estimator, okay. This is unbiased estimator of which of the given parameters. Okay, so this t, okay, the estimator, okay, okay, it is unbiased estimator of which of the given parameters. So I will start from expected value of this t. So this is expected 1 by n and wait, excise, oh, wait. Yeah, xi square, okay. And now this is 1 by n expected this summation xi square. Now this is 1 by n summation expectation xi square. And now this and this one. Wait, please. Okay. Now here this is equal to this, the linearity of E. Okay. Because of linearity of E. Now, expectation of sum and here sum of expectation. Here expectation of sum and here sum of expectation. How they are equal? This I have discussed in previous lecture. Please do watch that. And expectation of xi square, it is equal to this. Even this one in the previous lecture. And now this is 1 by n. And this is, wait. Yeah, so this is now sigma square and plus mu square. Actually, variance of xi, the variance of ith, single ith observation, sample observation, it is equal to population variance and this expected value of xi, the ix, it is equal to mu. And now this is 1 by n and this is I1 to n. So this is n times sigma square plus mu square. Okay, so this is now sigma square plus mu square. And what is mu here? Here, oh sorry, what is this one here? Actually, this one is our sigma or sigma square. So this is 1 plus mu square. Okay, so actually, if we are saying that our population X, it is following this tilde. Okay, so this is the tilde, this symbol. Okay, tilde. So if X means the population, okay, it follows the normal distribution, then the distribution, it has the parameters mu and sigma square. So what is mu? The population mean. And what is sigma square? It is population variance. Some authors, they say that mu and sigma square are the parameters, and some authors, they say that mu and sigma, they are the parameters of normal distribution. Means some authors, they say mean and variance, they are the parameters of normal distribution. And some authors, they say or they write that mu and sigma. So what is sigma? Standard deviation. Okay, that mu and sigma, they are the parameters. But here, whether this one, it is sigma square or sigma, it will make no difference, because if sigma square is 1 and if you take the square root, so it will be 1. Please mind, here it will not be plus minus 1, means it will not be minus 1, because standard deviation can never be negative. Okay. And now if sigma is 1, then obviously sigma square is 1. Okay. So that's why here, actually here the population standard deviation or population variance, the population standard deviation or population variance, it is known. Okay. What is unknown? Mu, the population mean. So that's why we are estimating the population mean. Okay. So here, this T, it is unbiased estimator of this parameter. Okay. And many results which I have used here. Okay. Rather, I think almost every result which I have used here, they are in the previous video. Okay. Wait, this. Now, there is a remark. Actually, if in binomial distribution, the number of trials, the number of independent Bernoulli trials, if it is equal to 1, then the binomial distribution becomes Bernoulli distribution. Actually, NCX, if I write B, X, and P, or this thing, probability that X takes the value X. Okay. So this is actually NCX, P raised to power X, Q raised to power N minus X. So here it is X. So what is this thing? These are symbols. So this is the probability that this expression, it is the probability that there are X number of successes, in N number of independent Bernoulli trials. I repeat this expression. It gives us the probability that there are X number of successes in N number of independent Bernoulli trial. So what is a Bernoulli trial? So first of all, what is a Bernoulli trial? Actually, a Bernoulli trial which results in exactly two outcomes. Okay, so one of them we will call term it as success, and another we will term it as failure. Okay, and what is the P here? It is this P. It is the probability of success. And what is Q? It is the probability of failure. Okay, so in our case, actually, suppose if xi, okay, if xi takes the value 1, then it is our success. Okay, it is success. And if xi takes the value 0, then it is our failure. So what will be P? This P, it is probability that xi takes the value 1. And what is Q? The probability that xi takes the value 0. Okay. So here, whether you use capital Xi or small xi, you may say here also that probability that small xi is 1, or here you may say probability that small xi is 0. It is the same. All means here there is no difference. Why? Because ultimately our sample observations, xi's, they are coming from where? They are from uh, uh, population itself. Okay. So in other words, that our ith sample observation. So, okay, I change here, okay, or jth, if I do jth here, okay, means our jth sample observation, it will be our some ith population value. Now, here one thing, uh, uh, I have stated this that usually the distribution of the population is known, that sometimes it is normal distribution, or that the population follows normal distribution, or Bernoulli or Poisson or any another one. Actually, how a population will have Bernoulli distribution? What's the meaning? What is, if I am saying that a population is having Bernoulli distribution, then the meaning is that we can turn we can turn any population into Bernoulli population. What's the meaning further? Suppose I have a city, say once again, say New York. Okay, New York is the city. Okay, now in New York, either a citizen of New York, it will have a sports car, or it will not have a sports car. Okay, I repeat, in any city, okay, in any population, okay, either the citizen, it will have the sports car, or it will not have the sports car. Now if the citizen, it has sports car, I say this is my success, that xi takes the value 1. And if it doesn't have sports car, okay, so here if I write having sports car, having SC stands for sports car, and here not having a sports car. Okay, so now what is my population? I have turned my population into Bernoulli population, because every population unit, either it can takes the value 1, means if the ith person, okay, it has sports car, and it is xi takes the value 0, okay, if the person doesn't have a sports car. So this is the meaning when we say that our population follows Bernoulli distribution. Okay, so actually all these things, they are from our daily life, but they do have meaning. So I will try that I can convey as much meaning as I can, okay, as I can now. Similarly, there are other examples to convert any population into Bernoulli population. Example, suppose now I have some another city. Say if I take the city of say Jalandhar city, the Jalandhar city in Punjab. That in Jalandhar, either someone is having iPhone or someone is not having iPhone. Okay, so if any Jalandhar citizen, if he is having iPhone, then it is my success. And if he doesn't have iPhone, then it is my failure. Okay, so we can define in a vice versa way, that if any citizen of Jalandhar, if he has iPhone, then it is our failure, that xi takes the value 0. Okay, I will say the xi. What is xi here? That any Jalandhar citizen. Okay, so if any Jalandhar citizen, if he or she has iPhone, then I will say that xi takes the value 0, my failure. And if he or she doesn't have the iPhone, okay, then it is my success, that xi takes the value 1. Okay, so that's how we can turn any population into Bernoulli population. Now, if in Bernoulli population this n it becomes 1, so what will this become? This one, it will be 1cx p raised to power x and q raised to power 1 minus x. And here x is 0, 1, 2, maximum up to n. Because here x, what this x represents, this random variable, it represents number of successes. Please mind. So here, everyone, if you are listening to this, please observe these values. Whatever I am telling you means observe my words very carefully. Okay, that here x, the random variable, it represents number of successes. So in n number of independent Bernoulli trials, okay, so what is the minimum number of successes? 0. And what is the maximum number of successes? N. Okay, so here if n is 1, so what will be x? X will be 0 or 1. Means in one Bernoulli trial, either I can have minimum no success, 0 success, or I will have maximum 1 success. Okay. Now here, this thing, 1cx. What is 1cx? 1. Because 1c 0 or 1c 1, it is 1. So what is this equal to? It is p raised to power x, q raised to power 1 minus x. And now what is this thing? This expression. This is the PMF, the probability mass function of Bernoulli distribution. This is the probability mass function of Bernoulli distribution. And what is this? This is the PMF. Okay, PMF of binomial distribution. Okay, now in binomial, these n and p, the n and p, what we call these n and p? We call the parameters. Okay, so now here, since n is 1, okay, means it is no longer a parameter because its value is known now. It is no longer a parameter because it is known now. It has become constant. Okay, it has become constant. So what's the only parameter here in Bernoulli? The only parameter is P. I repeat, in binomial distribution, the two parameters are n and P. Okay, but in Bernoulli, since n is 1, it is no longer a parameter. It is a constant now. So in Bernoulli distribution, what is the only parameter? P. Okay, obviously Q is equal to 1 minus P. Okay, we know this thing. Okay, so and what is P here? The probability of success. Okay, so for example, I was giving you this one that if someone is having sports car, okay, so here what's the probability of P, probability of success? Actually, it will be the probability that a citizen of New York, he or she has a sports car. Okay. Now, sum of an independent Bernoulli variates means variate or variable means if I conduct the Bernoulli trial. So Bernoulli trial is a single trial. Okay. So if I conduct a Bernoulli trial n times means I conduct it first time. Okay. So here if I write that I conduct it first time, then I conduct it one more time, then I conduct it one more time, total n times. Okay, I am conducting it n times. So what it will give, going to give me n. Okay, means now how many trials will be there? How many independent Bernoulli trials will be there? I repeat, if I am conducting single Bernoulli trial, single means n is 1, single Bernoulli trial, n times independently, then I will have n independent Bernoulli trials. So if the number of independent trials are n, then obviously we talk about what? We talk about this PMF, and this is the PMF of binomial distribution. So the sum of n independent Bernoulli variates is a binomial variate. Okay, so here it is written. So actually, x1, x2, xn, it is a random samples of size n drawn from a Bernoulli population. Now, I think you understand what is the meaning of Bernoulli population. If every population unit, if every population unit or every sample observation, it has only two options. Okay. So one of the options will be success and another will be failure. Okay. And with parameter theta, obviously, what is this theta? Here, theta is the probability of success. Okay. Yeah, here I use the ordinary, the regular symbol P. And actually, here it is theta. Means here, theta is nothing but P. Okay. Uh, and then this T, you can see this T. What is this T? It is sum. Sum of what? Xi's. What are Xi's? These are Bernoulli variates. Okay. And I1 to N. How many Bernoulli variates? N. And all these variates are independent. Okay. Because ultimately these Xi's are our sample observations. And our sample is it is a simple random sampling, means our sample observations are independent. So this one, okay, suppose I give symbol T. Okay. So this thing, okay, the sum of, the sum of n independent Bernoulli variates. It is a binomial variate. Okay. Means this T, it will follow binomial distribution with parameters n and theta. Here I told you that the parameters are n and p. Here the parameters are n and theta, because theta and p, they are same. Okay. Okay, one thing here, I am discussing in too much detail. So if one is not interested in this much of understanding these things, that what's the actual meaning of these, the real life meanings of these, and someone is merely focused about the questions, then he or she may skip this part. Okay. Now, we have a random sample of size n drawn on X, means drawn from a population which takes the value 1 or 0 with respective probabilities theta and 1 minus theta. Okay, so here what is theta? The probability of success. 1 minus theta, the probability of failure. Okay, then this one, this estimator, obviously it is a function of what? It is a function of sample observations. Okay, it is an unbiased estimator of which of the given parameters. Okay, so now, uh, obviously, I will start from, wait, please. Yeah, I will start from expected value of the t. Okay, and this is now expected value summation xi minus 1 divided by n minus 1. Okay. Obviously, why? Because he is asking me that this T, it is unbiased estimator of which parameter? Okay. So obviously, if expected value of T comes out to be the whatever the parameter. Okay. So this is now expected value T minus 1 divided by n minus 1. Okay. So what is T? T is nothing but this summation xi, which I have mentioned here. So now this is actually this n square minus n and expected t square minus t. Okay, expected value of t square minus t. Now this is equal to expected. Okay, and now this is mm, so actually. Uh, this is equal to this, okay, the linearity of E. And this one, it is nothing but equal to this. So once again, the same formula that I discussed in the previous lecture, that expected value of any square of any random variable, the expected value of square of any random variable, it is variance of that random variable plus square of expected value of that random variable. Okay. And now, what are variance of t and expected value of t? Okay, one thing, please try to learn these values. Oh, sorry, these things. Okay, try to learn rather than merely cramming. Try to learn. We should try to learn as much as possible. So, otherwise, there will be you will never have interest in all these. Okay, so now. N theta 1 minus and this and this. Actually, what is our t? T is a binomial variate. So what will be expected value of t? That will be n into theta. If you know that the mean of binomial distribution is NP, means if you have x which follows binomial distribution with the with the parameters n and p, then expected value of x, expected value of wait please, uh, yeah, yeah, expected value of x, it is np, and variance of x, it is npq. So whether you say the mean of x or the mean of binomial distribution, mean of x or mean of binomial distribution is NP, and variance of x or variance of binomial distribution is NPQ. They have same meaning. So now instead of P, what we have? Theta. Instead of P, we have theta. And instead of x, what we have? T. Okay, so that's why variance of t and theta 1 minus theta, and this thing is nothing but this. And now this is n square minus n, and here it is n theta minus n theta square plus n square theta square minus n theta. Okay, so this cancels now, and now this is. So n square minus n theta square. Okay. So you can see here that n square theta square. Okay. And minus n theta square, and this cancels. So what we have? Theta square. Okay. Means this estimator, this is unbiased estimator of theta square. And what is theta here? The probability of success. Okay. Option D is correct. So this is the last question, okay, for unbiased estimator. Uh, Let X be distributed in the Poisson form. Means here your distribution, sorry, your population is having Poisson distribution, okay, with the parameter theta. Okay. So first of all, actually, if he is saying that this theta is the parameter of this Poisson distribution, then probability that x takes the value x, it will be e minus theta, theta raised to power x divide into, And here x factorial means the PMF, the probability mass function of Poisson distribution is e raised to power minus theta into theta raised to power x by x factorial. If it is given that theta is the parameter of Poisson distribution. And this expression, it gives us the probability that, there are x number of outcomes. There are x number of outcomes, okay, whose average is theta, whose average of the outcomes is theta. And obviously here x, it can be 0, 1, 2, going on up to infinity, because number of outcomes, okay, I told you that here it is x is number of outcomes, so x can be 0 outcome, 1, 2, infinity, okay. So this is the PMF. Now show that the only unbiased estimator of this parameter, obviously this is a parameter. How? Because it is involving theta, the parameter. This expression is involving theta. Okay, so this is the parameter. And what is this? This is the estimator. Show that the only unbiased estimator of this parameter is this estimator. Okay, so obviously Tx will be positive if x is even, and Tx will be negative if x is odd, naturally, because what is k? K is positive. Okay, and what will be minus k? Minus k will be negative. Okay, now minus k is negative, you can see here. So if you raise to power 2, so minus k, if you raise to power even 2n, okay, then obviously it will become greater than 0. And if you raise to power odd, okay, means minus k raised to power 2 and plus 1, then it will be negative. Okay, I think you can understand this thing. For example, minus 3 raised to power 4, it is positive, but minus 3 raised to power minus 5, okay, sorry, minus 3 raised to power 5, that is negative. Suppose actually this question I have uh, try to convert it into a MCQ so that we can have a better understanding. So here, once again, we have to check that this parameter, you can see this parameter, it is for this parameter, which of the following is unbiased estimator? Means for this parameter, E exponential means E raised to power minus k plus 1 theta, which of the given estimator is unbiased estimator. So what I do, I start from this one, okay, A. So expected value of this Tx, okay. So what is that? It is expected value of minus k raised to power minus x. I start from this, okay. Actually, by now, if you observe carefully, okay, we already know that the answer is C option because it is mentioned here, okay. But still, for better understanding, I will start from here. So, minus k and minus x into probability, x is this and x, okay. Actually, in the previous lecture, I explained that expected value of any function of random variable, the expected value of any function of random variable, it is the values taken by the function into the corresponding probability. The values taken by the function, you can see what is this, the value of this function into the corresponding probability. Okay. Okay. And here x is from 0 to infinity, as I stated. So now here it is minus k raised to power minus x, e minus theta, theta raised to power x, actually obviously multiply, and even here and divide by x factorial, and x 0 to infinity. And now, next, Yes. This and e raised to power. Wait, please. Oh, wait. So this is e minus theta and theta upon minus k here x and x factorial. Okay, x0 to infinity. Means this e raised to power minus theta, I can take outside this summation because this summation, it depends upon x or it is with respect to x. It has nothing to do with e or minus theta. And you can see this here it is minus k raised to power minus x and here theta raised to power x. And so the basic calculation that we can combine them. Okay, you can see here. Okay, and x factorial uh, as it is. Now this is e minus theta and e raised to power this minus theta upon k. Okay, and this is now e minus theta common 1 plus 1 by k. Uh, e raised to power y. This is 1 plus y plus y square by 2 fact. Wait. Hmm. Okay, then y cube by 3 factorial and going on. Okay, so this is what we say that this is the Maclaurin's expansion. This is the Maclaurin's expansion of e raised to power y. Okay, so this we can write that this is a summation y. Okay, y raised to power say x divided by x factorial and x0 to infinity. That is okay. So if you put x0 here, then you will get this one. You put x1 here, you will get this going on. So what is y here? If you see, what is y here? It is minus theta by k. Okay, you can see here. Okay, so that's why e raised to power y. Now, it proves that this minus k raised to power minus x, it is unbiased estimator of this parameter minus k raised to power minus x. It is unbiased estimator of this parameter. But this was not our given parameter. Actually, our given parameter was this one. You can see here e raised to power, okay, exponential minus k plus 1 into theta. Okay. Now, what do you do? Just wait. Just give me some time, please. Yeah. Yes, this one. Now, for the option number 2, you can see here it is k raised to power minus x. So here it will be plus. So even here it will be plus. Okay. And even here it will be plus. Now, obviously, even here it will be plus. Okay, so even here it will be plus. Now, what will be here now? So instead of plus, it will be minus. Means e minus theta 1 minus 1 by k. This is the parameter for which this one, it is the unbiased estimator. But even this one, this is not the given parameter. Now, last option, it is nothing but this one. Okay, so what I do, I make the changes. Okay, just wait. So here, all the changes are there. So you can see even here, this change, even it will change here also. Even there will be a change. Even there will be a change. Okay, so Yeah. So it is minus k raised to power x. Even here, minus k raised to power, obviously here it will be plus x. Okay, now here minus k raised to power x and this theta raised to power x, but it will give you minus k theta whole raised to power x. Okay, so obviously here it will be minus k theta and minus theta 1 plus k. Okay, so this was the given parameter. Now you can see here, this was the given parameter means option C. Okay, this is the unbiased estimator of the given parameter. That is, whether you write that exponential minus k plus 1 into theta, or you write e raised to power this one. Okay, so thank you, everyone. Wishing you a happy journey of learning. Okay, thank you.